house coming from.
Yeah, maybe from 9:30.
Stop on the, it's actually the Bullock House. It's a stone house.
We're going to start there.
Yeah, so we're going to look at the stone in the stone house.
Yeah.
Postdoctoral research scientist at Columbia University and a visiting research scientist at Rutgers University. He is broadly interested in how the solid earth and climate interact to shape environments we observe on the earth through time, with a particular focus on Mesozoic, which is 251 through 66 million years ago. In addition to extensive field work, he leads several projects at the Rutgers Geological Core Repository and is a proponent of several proposed scientific drilling projects in eastern North America and beyond. So,
that sounds accurate. Oh yeah, this. Yeah. I'm fine with them on, but I think the pictures show up a little bit crisper when they're. Oh wow! All right, can everybody hear me? All right. Okay. Cool. All right. Everybody good? We're good. I guess we're good. All right, hey, well thanks Candy and Jim for the introduction and for inviting me here today. Like Candy said, I'm Sean, a postdoc at Columbia and a visiting research scientist at Rutgers. And I'm just going to give you a couple slides introducing myself so you kind of have a sense of how I approach geology and the lens that I'm viewing the rocks through around here. That's also going to shape the structure of my talk thematically, and also a little bit our field trip for those of you who are going on the 6th or the 7th, which is the rain date, right? Okay. There we go, cool. So I did my undergraduate degree at Rutgers almost 10 years ago now in geology, and when I was an undergrad I spent a lot of time working in the structural geology modeling laboratory. So for those of you who don't know what structural geology is, that's kind of like engineering applied to geology and figuring out how different kinds of materials deform when we apply stresses to them. And then I switched gears almost entirely when I got to grad school. I did my PhD at Columbia, where I'm still at. And the focus of my thesis was trying to understand how some rocks up in New Hampshire fit into the broader set of processes that were happening, as the supercontinent Pangaea split apart almost 200 million years ago. To do that, I spent a lot of time collecting samples in the field. That's a pretty typical view up in the White Mountains in New Hampshire for those of you who are familiar with the region. That's the Redstone Quarry for those of you who are very familiar with the region. I'm not sure how many White Mountain folks we have here, but I figured I would throw that in there. And I spent a lot of my time down the road at Princeton during grad school as a visiting grad student doing zircon uranium lead geochronology in a laboratory there, where I would take a rock, break it apart, separate out the mineral zircon, measure isotopes of uranium and lead to be able to produce an age for the rock. And that's how, one of the tools in my toolkit that I use to try and figure out and relate how these rocks up in New Hampshire relate to rocks here, and as you'll see in a bit, around the globe. And this has led to some published papers and some papers that are still in the works, looking at, like I mentioned, how these rocks up in New Hampshire relate to much larger scale processes and large scale magmatic provinces, which I'll also introduce in a second, but also old hotspots. So those of you who are familiar with Hawaii, looking at the remnants of a hotspot that North America passed over, much like the Hawaiian Islands formed. This is 100 million years ago. I'm not talking about that today. And throughout grad school and throughout my undergraduate years, I've spent a lot of time doing events just like this, going on tours, giving tours, leading workshops, having outreach events. So I really enjoy doing these things. It's really great to be back after COVID and not having done any of these things. This is my second in-person talk in almost 4 years, which is kind of hard to believe. And the first one was only 2 months ago. So it's good to kind of be back in a room full of people and being able to talk with you here. And I'm just going to throw out there now, if any of you want to talk further after here on the trip on May 6th, or you can Google me and email me as well. So I'm really open to continuing the conversation. one of the things that I switched gears on in grad school was going from looking at igneous rocks, which are rocks formed as a result of magmatic processes, so you could think of volcanoes and their constituent parts, to looking at sedimentary systems, which is the majority of what's around us here in Montgomery Township. I spent a lot of time looking at rock cores that were collected from just around this area, and I'm going to be talking a bit about that later in the talk, and using a machine. Does my laser pointer show up here? Yeah, it does. This is a XRF instrument, X-ray fluorescence, where we can shoot high-energy X-rays at any material, in this case rock, recovered in core, and be able to tell something about the composition of that rock. I'm going to talk a little bit about that later as well. And that's led to a successful proposal, which is funding a lot of the work that I'm doing right now, trying to understand ancient solar system dynamics through continental records of climate change on Earth from 200 million years ago. And that's going to be the main locus of this talk. In a bit, I'm going to go through some background and introduction first. So all of this work takes place at the Rutgers Core Repository, and many of you may not be familiar with core repositories or the fact that Rutgers has a core repository. At our facility, we have, and this is not an exaggeration, tens of kilometers of rock core stored there, both rock and sediment core. The rock core, the majority of that is collected from right here in New Jersey, in and around what's called the Newark Basin, and I'll introduce what that is in a bit. But there's also several sediment cores taken from what is the New Jersey coastal plain, looking at records of sea level change and climate change throughout the more recent past. And by recent past, I mean 66 million years ago to the present day. So in the lab that I run there, we have this instrument here called the Minimalizer. It sounds like something very sci-fi and maybe out of Terminator. But it's another type of core scanning X-ray fluorescence machine where we can look at the composition of rocks, and we also have other kinds of what are called spectroscopic tools. We apply different kinds of spectroscopy to look at the different properties of these rocks to say something about how they formed and how that relates to some of the bigger picture questions that we might want to try and understand in geosciences. This is pretty typical of what rock cores from around here look like. This is a split core from the Colorado Plateau. These are CT scans, computed tomography scans. So this is, I'm not kidding, sticking core into a medical imaging device and trying to look at its three-dimensional structure and being able to try and understand how different aspects of its structure might relate to porosity or permeability or something about the environmental conditions in which the rock formed. And we have a lot of projects going on right now. And like I said a couple minutes ago, please reach out to me if I say something that I don't really go into, but you'd like to learn more about it, reach out to me, I'm happy to talk more about it. This is a very small set of examples of the kinds of things that we're working on, but we're trying to understand something about climate and solar system dynamics in our lab. We're looking at things like geogenic contaminants in bedrock. Raise your hand if you have a reverse osmosis system and you're on well water, because there's arsenic in it. Okay, so some of you do, yeah. So that's due to bedrock control of arsenic that's in your aquifer system that your well is tapping into. So we're trying to understand the distribution, both vertically in the rock subsurface and laterally in the rock subsurface, and trying to understand how those metals move around and what are the conditions that facilitate their mobility, both here in New Jersey and on the Colorado Plateau. And we're also trying to understand something about critical minerals. How are they formed? What concentrations are they in different environments? You can see this orange here. I was up in northeastern Pennsylvania last Friday, looking at acid mine drainage and trying to see what we can do to also remediate abandoned mine lands. And we have a large component of our work is remediation of abandoned mine lands, but in a way that's also potentially economically productive for the people whose lands are contaminated. And we spend a lot of time training students in the lab and getting them training in lots of different kinds of both geological practices, but also analytical practices. So we have a pretty dynamic research group. And what I'm mostly going to be talking to you about today is in the box on the left, which is climate and solar system dynamics from the rock records that we're standing on and that are all around us. This is one of the only slides with a lot of text because I really don't like text slides, but this outlines the general narrative of the talk that I'm going to be giving today. So the rocks and sediments of New Jersey host an over 1 billion year record. That's actually pretty incredible. You wouldn't think. Everybody kind of rags on New Jersey, like, all this is stinky industrial areas and the turnpike, but there's actually a lot of really interesting stuff here and a lot of opportunities to understand fundamental processes in the earth. And when we do detailed study of those records, we can get some insight into really, truly strange, but also large-scale processes that New Jersey probably has some of the best records on which to study. Coring provides the opportunity to recover much longer records and capture the processes we want to understand over much longer timescales. You've probably driven around here. It's not like we're out in Arizona or Utah where there's cliffs and exposed rock. There's a lot of information that's hidden under the subsurface. There's a lot of information that's gone away. Coring is one way that we can recover records, to study them, to be able to get fresh material, to get continuous material, to get material that we have a much more unambiguous sense of where it is spatially with respect to other rocks. Cores from the Newark Basin reveal an unprecedented record of astronomically paced tropical climate change and provide the opportunity to understand ancient astronomical processes. That's pretty loaded, but it's true. The record that we have here in New Jersey that I'm going to talk to you about is the longest continuous record of continental tropical climate change anywhere on the Earth, and it's what we're standing on right now. Local records visible in core and outcrops like those in Montgomery Township provide unique windows into the past and a means to understand our journey through space and time. It's true. The rocks we're standing on are unique, and in terms of the completeness of the record that they are a part of, are unlike any other record in the world, which is pretty cool. So, to orient ourselves, I'm throwing up this concept of the cosmic calendar. I don't know how many folks in the room have seen the 1980 version of Cosmos by Carl Sagan, and this is a concept that was introduced there, and that's something that really inspired me to go into science, but this is, I think, a really useful way to try to get a sense of time and a reference. There's lots of ways that I could do this, right? I could bring in a piece of tape and go from one end of the room to the other and draw a line at the end and say, well, all of human history is in that little, millimeter thick line at the bottom of the piece of tape in terms of if we were to squish all of time, 13.8 billion years ago to the present, into a single calendar year. So if we do that, starting in January with the Big Bang, Milky Way forms somewhere around May, the solar system forms in September. October, we have the first oxygen here on Earth. November, eukaryotic cells. December, multicellular life. Wow, we're running out of time in the year, right? Then we get into the second week of December. We have trace fossils and body plans of the earliest multicellular life. Bones and shells, December 17th. And then we really don't get into the kinds of organisms that we're familiar with now, walking around, until December 18th. We don't get dinosaurs until Christmas, December 25th. Mammals on the 26th, birds the 27th. December 30th, the dinosaurs go extinct. We are really running out of time in the year, right? And then on the final day, we have evolutionary processes that are occurring that shape our ancestors and us, leading us to the final minute, where we have the earliest cave paintings about 50 seconds ago, and the peak of the last ice age, and I'll show a cool little figure in a second to give you a sense of scale there. We have the first Egyptian dynasties 15 seconds ago, all the major biblical figures about 5 seconds plus or minus 1 second, and the first American colonies, so right around when Montgomery Township was founded, about a second ago in this cosmic calendar. So not a lot of time for things that we're familiar with in terms of the entire history of the universe, which is kind of cool to think about the scale of things in that way. And a little humbling, too. So, geologists like to think about things in terms of the geologic timescale. And we don't start the geologic timescale until the solar system is formed. So we're already in, what did I say? September? By the time we get to where the geologic timescale begins in this concept of the cosmic calendar, 4.5 billion years ago. Solar system forms. So late October, about 2,500 million years ago, 2.5 billion years ago, that's when we start to see an atmosphere that looks kind of like our own with oxygen. December 15th to 16th, we get these strange, funky looking things that show up in the sedimentary record. I don't know if you can see those up there. This little shape there, these little shapes here. This is from a place that I really recommend if you can get there, called Mistaken Point Fossil Preserve. It's in Newfoundland, and it's I don't think it's formally a UNESCO World Heritage Site, but this is what makes it a candidate for being a UNESCO World Heritage Site, because it's one of only a handful of locations on the globe where you can see this first earliest evidence of multicellular life that shows up in the fossil record. 500 million years ago, we get this explosion of complex animals called the Cambrian explosion. And I found this photo online. I thought it was the Big Bang of the Cambrian explosion. So all these animals that are floating around. There we go. Sorry, there we go. This one here. The oldest fish that we might recognize swimming around today, December 20th. Pangea forming on Christmas. And then the top photo I have there is the impact structure in the Yucatan Peninsula in Mexico, which is the location where the asteroid that killed the dinosaurs impacted the Earth. So I'm going to, again, kind of bring us back into this reference frame of the cosmic calendar and just go through the last 60 seconds. So 45 seconds ago, in the cosmic calendar reference frame, we have major ice sheets. If you were to go up to the top of the Sourlands and look towards New York City, you would have ice sheets that are about 2,000 feet thick. And that's a sense of scale for the skyline you might see. Now, I think on a clear day you could see the skyline from the top of the Sourlands. But you'd see something that looks like that instead. Pretty scary. 25 seconds ago, and about 12,000 years before the present, is the arrival of the Lenni Lenape peoples in the area. The last 2,200 years is condensed to about 5 seconds in the cosmic calendar. Again, switching back to the geologic timescale, this is just the last 2.4 million years represented in the geologic timescale. Right now we're in a period called the Holocene. Some would argue that we're in a brand new geologic period called the Anthropocene, which is when we can start to see the effects of human activity on the planet begin to shape it more than natural forces. But everything that's in this last 60 seconds, you can barely, I didn't even bother drawing a line because you wouldn't be able to see the line because it's right there and up. A very small fraction of just the last 2.5 million years. So let's go to milliseconds. So let's go to the last second. 1,000 milliseconds ago, we have Verrazano's cruise up the East Coast in 1524. We have the Dark House at 620 milliseconds ago, 1752. The Battle of Princeton, where Washington marched his troops right through Montgomery Township, if I'm understanding my Montgomery Township history correctly, is about 550 milliseconds ago. The incorporation of Montgomery Township, 1798. DNR Canal opens, 1834, about 450 milliseconds ago. Route 206, big things are happening. 1927, about 220 million years ago. And brings us to about the present day where, I'm going to say, it's still 22. It feels like it's still 2020, but you know, the present day, the building that we're standing in opened. And when we look at maps, when we look at geologic maps, these maps are color-coded, and this is not the colors that you see on the map. Why can't I get my orientation on this laser pointer right? The colors that you see on this map do not correspond to the colors here. That's just the time scale that I use, but they do correspond to the units right here. And those colors are telling us something about the age of the rocks and their distribution throughout the state. And every state has a geologic map, and all throughout the world has been mapped, at least to a first order. Some maps are more complete than others, we'll say. And there's 4 distinct portions of the state just based on the ages of the rocks that underlie it. In the oldest part of the state, the northwest corner, sorry, I think I have slides here, my presenter view isn't here, so I actually don't know what's coming next. So we're gonna wing it here, yeah, there we go. The oldest part of the state is in the northwest corner, so you could think of Sussex County, thereabouts. And these are rocks that are often quite deformed. They contain records of the oldest life. These kind of strange-looking mounds on the top right are something called stromatolites, which are the records of mounds that were built by cyanobacteria. Cyanobacteria themselves were also responsible for generating oxygen in Earth's early atmosphere. If anybody's been to Franklin, New Jersey, and been to the Sterling Hill Mine, which I highly recommend everybody get to at some point because there's lots of cool stuff there. You can see these beautiful fluorescent minerals that are over 1 billion years old that were formed in an ancient mountain building event. And you can see the tilted strata at the Delaware Water Gap, which you can see, hopefully this shows up okay for you. The beds here are tilting almost 45 degrees to the bottom left of your screen. Incredible forces go into shaping and deforming the rocks that are around us. Geologists like to think in, and I'm going to apologize in advance, geologists like to think in these columnar ways where the oldest, something that we're trying to say in time, is typically at the bottom, and we go to the top in the direction as it youngs. So the oldest, so this is just a very rough schematic showing you the amount of time that Eastern North America experienced mountain building events. And geologists have all kinds of fun names for these things. They name all the different mountain building events that are present in the geologic record. The oldest is this Grenville orogeny, which happened over 1 billion years ago, and then during the period of time just before what we're going to be talking about and focusing on today, there were 3 other principal mountain building events or orogenies. If you hear me say orogenies or mountain building events, I'm talking about the same thing. And I'm going to be clarifying. I tend to slip into different words, saying the same thing 10 different ways. So I'm going to do my best to clarify that when I do that. And these mountain building events lasted from about 550 million years ago all the way up to 300 million years ago. And that shaped the rocks that we see primarily in the northwest part of the state that are very deformed, tilted, faulted, but also provide the pre-existing zones of weakness that the younger rocks took advantage of when Pangea split apart. And I'll talk about that in a second. Flipping to the other side of the state, again, this is all just for context to show you how the rocks that we have here are different than the rocks that we see elsewhere just in the state, and how we have a lot of dynamic processes that shape the history of the state. This is a cool little video showing you one of the best places in the world to see the boundary at which you can put your hand on one rock. Well, it's actually not a rock, it's more like sediment. It's very unconsolidated. Below the boundary, dinosaurs existed. Above the boundary, dinosaurs no longer existed. Okay? And that's right here in New Jersey, in Millstone. And it's also, New Jersey has one of the best records of long-term sea level change since the Cretaceous. So a lot of what we understand about global sea level records for the last 60 million years come from work that's been done on the New Jersey coastal plain. And I'm taking the opportunity to plug something called the Rutgers Virtual Geosites. So if you have a QR code on your phone, I hope these QR codes still work, but there's a group that I work with that has put together really great drone tours of different sites throughout New Jersey. I think this started as a COVID project and then built out into something much larger and something with a really good potential to reach a lot of people with interesting things. And I'm going to have a couple of these throughout, so keep your eye out for them, and please scan them, or if you miss them, let me know, and I'm happy to send you a link to them. So, moving in to the center part of the state, which is where we are, and where we're going to focus the talk, we see rocks that look nothing like any of the other rocks or sediments that we have in New Jersey. We have these big cliffs that, that you've probably driven across the George Washington Bridge and have seen the Palisades cliffs. Or maybe you've been to Paterson, New Jersey. Again, sleeper on the tour, but you got to go, and you got to check out Great Falls National Historic Site and go to the Paterson Museum if you're interested in state history and local history in general. Really, really interesting stuff. And I'm biased. I've been living the last 10 years up here, and I just moved to South Jersey. So most of my geological photos are in and around a 5-mile radius of Englewood, New Jersey. So, but we can go out to Milford, into Pebble Bluffs, if you've ever been out there, and see these big cobbles that are in the sediments that look nothing like the very fine-grained rocks that are in and around Edgewater. And actually, those rocks there are the same rocks that we're standing on. Well, not quite the same rocks that we're standing on, about the same rocks that we're standing on right here we're in Montgomery Township. Right now? Yeah, in Montgomery Township. So all the rocks that are in this part of the state formed during, not just, they formed during the Mesozoic, but they formed during a specific time period within the Mesozoic called the Triassic. And that lasted from about 252 million years ago to 201 million years ago. So this is about a 50 million year period of time. And it's interesting for a lot of reasons. If you care about life, it's when all of the major animals that are running around on land today came onto the scene. If you like mass extinctions, it's when a lot of animals that were around during the Triassic died at the end of it. And if you like large volcanoes, some of the largest volcanoes that ever existed during the Triassic. So, how did all these rocks form in this part of the state? So, we're going to go back in time to Pangaea. This is about 201 million years ago. And at this time, all of the continents that we know today are sutured up into one large supercontinent. This is a little animation that shows you from where they are together to how they eventually reach their current configuration. I like these little animations. I'm going to leave this go for a second, just so you can get a sense of both the time, which is at the top, in MA, which is millions of years. So this begins at 251 million years ago and ends at the present day. And you can see most of the continents are squished together at the beginning, at the equator, and then they eventually gradually move north as they come apart, and North America moves even farther north. So starting out about the equator, and then moving to the present day position we're in today. And this is a very generalized geologic map of where we're standing. So the first inset here shows you these kind of elongate features that are scattered throughout the eastern North American margin. So this is North Carolina, going up through Virginia, Maryland, Pennsylvania, New York, Connecticut. Up here, this is the Fundy Basin in Nova Scotia. And these are all records of ancient lakes that formed at the time that the supercontinent Pangaea was splitting apart. And at the very end, and we actually, I'm saying this, but there's nuance that I'm not going to get into. At the very end of this process, or near the end of this process, one of the largest series of volcanic eruptions ever to occur on the planet happened, something called the Central Atlantic Magmatic Province. And I'll show you a slide in a second on that, but this figure here shows you the two different colors. The darkest color here are what are called igneous intrusions, so you could think of these as liquid magma that never made it to the surface that we have evidence of. The slightly lighter shaded region is the estimated extent of lava flows that were associated with this province. So this is massive, massive. And we'll talk a little bit about how massive in a minute. And this, and I'll be showing you snippets of this later on, is the geologic map of where we're standing on this rift basin right here, number 1, the Newark Basin. Oh man, I can't get my pointer. Right there is this right here. And these different colors are just telling us what the different rock types are. I'm not going to get into that in detail, but the thing to take away is that this is complex. You see that these rocks kind of have an organization, but that organization is split up in different places, and it has to do with tectonic forces that have deformed it after it formed. And I'll show some color maps in a little bit that will go into slightly more detail, but you don't really need to know the details to just have a sense of this is an elongate structure. It was a lake when it existed. That lake existed when Pangaea split apart. And the sediments that were deposited into that lake eventually became the rocks that we're standing on right now. That's a gross oversimplification, but that's the gist of it. So I mentioned this thing called the CAMP, the Central Atlantic Magmatic Province. 11 million square kilometers of eruptive material, which is incredible. Somewhere on the order of about 2 million cubic kilometers of lava. Huge. Very spatially extensive, all the way from Europe to South America. The southernmost occurrence is in Bolivia, and the northernmost occurrence is in France. So we're talking thousands of kilometers in distance. And what's really, really interesting about this, at least to me, as somebody who likes to date things, as somebody who likes to try and understand these big tectonic processes in the Earth, is that all of this, that 11 million square kilometers, 2 or 3 million cubic kilometers of lava, all of that happened in less than 1 million years, which is very, very short. I know it sounds like a long time, but it's incredibly short when we think about the kinds of processes that are involved to make these big types of things happen. Okay? What's also interesting about this is that large series of volcanic eruptions coincides with one of what's called the Big 5 mass extinctions on planet Earth. So we are all probably more or less familiar with the mass extinction associated with the demise of the dinosaurs, thought to be the result of an impact. This one, at about 201.5, we could get very, very precise and estimate down to the calendar day, but we actually can't. But at about 201.5 million years ago, another major mass extinction happened. On land, essentially killed off all of the major, large cold-blooded reptiles that were walking around and cleared the way for dinosaurs to take over and diversify and eventually rule the planet for the next 140 million years until they met their demise. And this is all, again, within the context of Pangaea splitting apart and the formation of the Atlantic Ocean. And it's unclear how this large, what the timescales are on these things. Did the Atlantic Ocean form at the same time as this? Did it take 30 million years? These are actually open questions. We don't have good constraints on when rifting ends, when what's called drifting begins, so when the continents really start to pick up speed and move apart from each other, and what we call seafloor spreading and the formation of new ocean crust beginning. We don't really have good constraints on that. What we do see are these kind of funky structures offshore. Let me orient myself again here. There's a large magnetic anomaly that shows up off of eastern North America, which is probably due to fairly dense rocks, iron-rich rocks, things like basalts. And when we look at the interior of the Earth through something called seismography, so the way that we produce an image like this is ships go off the coast of wherever they're leaving from, in this case, New Jersey. Ships sail out into the ocean, they drop charges, something that bounces sound off of the bottom of the ocean floor, and it looks at the time that it takes for that to get back. So you can think of this as kind of a sonogram of the interior of the Earth. And what we see on these kinds of images are these, and you can't really see it all that well, are these kind of strong reflectors that are dipping offshore. These are volcanic units. We know that they're probably in some way associated with the opening of the Atlantic Ocean, but we don't really know how they fit into the Central Atlantic magmatic bonds. We don't know what the timescales are. We don't know how this relates to the formation of the Atlantic Ocean. There's lots of open questions that are unanswered, largely because some of these records that could be useful are gone. They've been uplifted and eroded, or they're inaccessible. These are several kilometers beneath the ocean floor. It's very, very difficult to drill down and recover materials that might be able to give us better insight. So is there any place on Earth where we can go and we can see similar processes that are happening today? Yes. So we can go to East Africa, and you can notice some similarities just by looking at this image. You see these lakes that have very similar geometries. I'm going to tell you, we can't really see all that well here, but there are volcanoes that are scattered up here. There's igneous activity that's happening. Magma's moving through moving through the mantle into the upper crust, erupting out onto the surface. Continents are splitting apart here. So this is kind of similar. This is what we call a rift zone, much in the same way that the rocks that we are standing on formed in a rift lake. These are rift lakes. It's Lake Malawi and Lake Tanganyika in East Africa. And you can see, this looks very broadly similar to the kinds of features that we see that are remnants of the ancient rift lakes that existed here 235 to 200 million years ago. Interesting. This is just another shot of Lake Tanganyika. And this you can't really see all that well, but this is the kind of landscape that we might expect to see. You can see these lineaments in the Earth's surface. These are faults. You can see in some places where they intersect, you get these lakes that form. And you can see these kind of irregular features that are popping up onto the landscape. And those are volcanoes. So this is kind of what we would maybe see here 200 million years ago. So in the most abstracted way possible, what's going on, how do these lakes form? You have extensional forces in the crust that are pulling the crust apart. Big holes form. Rain happens. Those lakes fill up with water. And in the simplest way that I kind of want you to have in the back of your mind as we move forward is any changes that we see in the level of these lakes that form along these faults are almost entirely due to changes in the amount of precipitation that's going into them. So how much is it raining? And that's going to be a function of climate. That's an oversimplification, but for our purposes here, have that in the back of your mind as we're moving forward. And again, there's a QR code. You can learn in very, very detailed with, I think, a 3D drone tour as well. Or if it's not there, it's coming soon. And the amount of precipitation that is ultimately going into these lakes, much like today, this is true for East Africa, it's true for these lakes, because if you remember from the animation that we showed of the continents together around the equator 250 million years ago, we're very strongly influenced by the monsoonal climate that exists. That monsoonal climate is very strongly influenced by small changes in solar energy that's received. So you change a little bit of solar energy that's received in those areas, you change a little bit of the precipitation that occurs. This is a very basic model, but keep this in your mind. So what did these landscapes look like 200-ish million years ago? This is, and I highly recommend you check this artist out, William Sillam. He's done a lot of both paintings as well as digital art of Mesozoic landscapes or Earth history landscapes. This is what one of these lakes may have looked like, not unlike the Newark Basin, which we're standing on, or any one of these other rift lakes up and down eastern North America. big mountains in the background. And again, if you remember the photo I showed you of East Africa before, these are these big faults that are forming. Those lakes are forming along the boundaries of those faults. And critters like Dilophosaurus are running around, going about their day, and looking for food, fighting with other Dilophosaurus. Whatever a Dilophosaurus does, I don't know. What do chickens do? Maybe we have some insight into what Dilophosaurus did. And you might be familiar with Dilophosaurus from Jurassic Park, which is one of the dinosaurs. I think it's Newman's character. If any Seinfeld fans remember Newman, Dennis Nedry is his name in Jurassic Park, but he meets his demise from a Dilophosaurus, which is one of the most common animals that would have been running around in these lakes 200 million years ago. And also one of the most common fossil tracks that you can find in these lakes. And this is just another landscape, but I really like this one because I think the colors are great. I think the scene is cool. You have all these animals that are just, it's like if you were to go to a lake now and look at the birds that were walking around, or maybe some turtles, right? They're just going about their day, living their life, looking for food. And again, slightly different environment. This lake looks a little bit shallower than the one that we saw before. But again, these big mountains in the background, maybe these are some storm clouds, the monsoon's coming in. And maybe this kind of haze here is this reddish-orange haze is a sense of foreboding. Maybe some volcanic eruptions are causing the changes to the composition of the atmosphere. And we're getting the beginning of the Central Atlantic magmatic province. What do those sediments look like today? What do these environments look like today? This is now our environment. We're going around, driving around, looking at rocks. This is what we see. This is what's left over from the sediments that were deposited in these lakes. And we see kind of interesting things about this. We see what look to be maybe some patterns that repeat themselves. You see the repetition of this very dark unit. Here. Again. You kind of see it maybe up here. It's a little bit obscure, but where these trees are growing out as a bench, you can see it again. It becomes much more faint up here. And then we see another very dark unit popping out up there. And there's this almost cyclical rhythm to rocks, especially around here, and especially in certain places in the Nereid Basin, that are very eye-catching. And this is something that's been known for a little while. And we see, so this is in Pennsylvania. I should say that this is from Pennsylvania. This is from a quarry in the Eureka Quarry in Bucks County, PA. And this is the same quarry, a different angle. And again, you can see, I'm not sure how washed out the colors are. I'm colorblind anyway, so I do my best. But you can see a black shale here, another black shale above it. It gets a little fuzzy, but you can see a color change right here, and then you see another black shale here. And you see this repetition of dark to slightly lighter, back to dark again. That continues at a very large scale. And the best outcrops of being able to observe these patterns exist in quarries. You really only get snippets of it in the best possible places where they're on the side of the road, or maybe along a road cut if you've ever driven up Route 29. These are the rocks that you see. They shape the patterns that you see in the landscape. And depending on where we are in time, this is 217 to 222 million years ago, depending on the overall state of the climate system and how precipitation is changing through time, as the strength of the monsoon is changing through time, as the climate is influenced by lots of different factors, the character of that rhythmicity and cyclicity and the colors that you can see and the types of textures that you can see in the rocks also changes. You notice the previous slides, alternating gray, black patterns. This is completely different. This is red. We see some textural changes in the rocks, but it's much harder to pick out the cyclicity in these rocks by being able to say, there, I see a black line of rocks here, I see another black line of rocks above it. It's a little bit difficult, but it's there. This is probably the best example of this kind of cyclicity. This is from what's lovingly dubbed the Grand Canyon of Connecticut, right near Dinosaur State Park. which if you've ever driven up Route or Interstate 91 between New Haven and Hartford, it's about halfway. It's about the halfway point. So if you're ever doing that drive, I encourage you to stop off and see one of the largest and probably best preserved fossil trackways of dinosaurs that were living at this time. Probably anywhere in the world. It's really a world-class site. But here you can see this dark layer into a slightly grayish purple layer, into a red layer, back up into this darker layer, and repeating itself. And we see that same kind of basic pattern extending in either direction with slight modifications, and those modifications become important. And the basics of this were worked out over 60 years ago now. First by Franklin Van Houten, who was a professor at Princeton. Some of you in the room may have known him. And he spent a lot of time walking Route 29, looking at these patterns in the rocks, and trying to figure out what's their origin. What are the processes responsible in the lake that are producing these changes in the sediments that we see as now changes in the rocks. A contemporary of his, Dean McLaughlin, who is a professor of astronomy, as his summer hobby, would come to beautiful Hunterdon County, New Jersey, and spend time mapping the bedrock geology. Not really focused on the origin of the patterns of the cycles that he saw, but was able to delineate them in geologic maps very, very well. Van Houten intuited a bit about their origin and said that it has to, these have to be from some kind of external origin, perhaps astronomical in origin. And the best way that these have been characterized, and which was the really test of the hypothesis of how these cycles originated, was worked out by Paul Olson back in starting in the 70s and then through the 80s and continuing to the present day. Paul was my PhD advisor. And he came up with this system of qualitatively characterizing, or semi-quantitatively characterizing, the sedimentary fabrics of these rocks. So looking at the textures of the rocks, coming up with some set of criteria where they can be ranked relative to each other in terms of the depth of the water that they were deposited in. So what do I mean by that? What I mean by that is, and I'm going to talk about end members, what are the set of criteria that I can use to describe a rock that allows me to infer that it was deposited in the shallowest state of that lake at the time that it existed. On the flip side, what are the characteristics that I can use to describe a rock that was deposited in the deepest possible state of that rock? And defining criteria for these intermediate states allows us to be able to look at how lake level changed through time, as a function of time. So I'll show you what I mean by this. So we're going to go back to the quarry, Eureka Quarry in Bucks County, Pennsylvania. And I mentioned before, geologists like to show these long columns. So the bottom of this column is the oldest part of the record. The top of this column is the youngest part of this record. And this is just a way of, on the left, very generally showing how the lithology or the character of the rock or the rock type changes as you go from bottom to top, or oldest to youngest. You apply this depth rank classification scheme to those rocks, you can generate something that looks like this, which itself is a signal. So starting at the bottom, alternating 0 to 5, 0 to 5, 0 to 5. So what this is representing, what these changes are representing through time, in terms of the thickness of the rock, is how lake depth is changing through time. And we see this pattern of shallow to deep, and back again throughout the entire length of the record. And this is just a much more blown up view of what 1, 2, 3, 4 of these cycles looks like. So you see deep to shallow, and a little deeper here, deep then this basic pattern repeats itself again. Come on. There we go. So, abstracting this a little bit and showing a sketch of this basic cycle, this basic pattern that we see repeating itself through the rock record in the rocks that we see around here. This is something that Paul Olson named the Manhattan cycle after Franklin Manhattan, is the characteristics that we can use to describe the rock and the depth of the lake in which the sediments that form the rock was at the time that the sediments were deposited. Going from a very shallow lake to a very deep lake, to a lake that's shallowing out, to the lake that's at its shallowest possible state, and then the cycle repeats itself. And that's reflected in terms of the fabrics that we can see in the rock, in terms of the kinds of fossils that we can see in the rock, in terms of the chemistry of the rock, in terms of the grain size that we see in the rock. Because all of these things are telling us something about the hydrology, about the climate, about the kinds of animals who would have been living. You know, the dinosaur is not going to be swimming in a very deep lake. We're not going to find dinosaur footprints if that lake is very deep. We're also not going to find very well-preserved fossil fish in a very shallow lake, or a lake where it's almost dried out and we're beginning to form soils. So what are the kinds of processes that might lead to cyclical variations in depositional process, cyclical changes in climate in general? And I hope that these animations work here. This is just kind of a thought experiment, right? So, let's start with taking things that we're familiar with, right? We have the Earth going around the sun, spins once every 24 hours, about, and we can certainly have, where there's night and day that causes temperature changes. That could be one way. There's also, animations. Tidal cycles. There we go. And anybody who's been to the beach has seen these. I thought this was a cool map that I found, showing annual cycles, right? And this is showing it very dramatically as changes in sea ice at the Arctic. But you can see there's also changes in how green it is around the equator, and that's just changes in what's called the intertropical convergence zone each year, where its position changes. There's also solar cycles, sunspot cycles. But, just keeping this thought experiment in mind, if I tell you, just outright, sediment accumulates at the bottom of Lake Tanganyika, which we said was a good analog for the kind of lake that the Newark Basin was. It accumulates at a rate of about 1 millimeter a year. And the cycles that we see in the rocks today, that are left over from the Newark Basin, are on the order of the smallest cycles that we can see in outcrop, are 4 to 5 meters. Does any of these familiar processes make sense to produce the kinds of cyclical patterns and changes that we observe? So what kinds of things are going on longer time scales, maybe astronomically external to the Earth's system, that can regularly and periodically change climate to affect the amount of precipitation that's happening, which is in turn affecting the depth of these lakes that existed. So hopefully these animations work too. Everything seems to be working okay. So to really get at this answer, we need to think about changes in Earth's orbit and changes in planetary scale processes that are affecting the geometry of Earth's orbit, how it's moving around the sun. These are what are called Milankovitch cycles, named after a Serbian mathematician, Milutin Milankovic, who worked at the mathematics of this back in the 20s when he was in, maybe the teens, when he was in prison during World War I. And what these are periodic changes, so in different parameters of Earth's orbit, the shape of Earth's orbit. So the longest of these shorter Milankovitch cycles, and I'm going to talk a little bit about longer Milankovitch cycles, but we'll start here. About every 100,000 years, the shape of Earth's orbit goes from being almost a perfect circle to slightly less than a perfect circle. These are very subtle changes in how circular Earth's orbit is. About every 40,000 years, the tilt of Earth's spin axis changes by a couple degrees, by about 4 degrees. And then about every 26,000 years, if you've ever spun a top and you've seen the wobble of the spin axis change, precesses. Earth's spin axis precesses with a period of about 26,000 years. To show you what this looks like, I promise I'm trying to avoid showing all these nasty graphs, but to just show you what this looks like, these are the parameters that describe how eccentricity, how tilt or obliquity, and precession change. And you can see that they vary. They have regular periods. And what I have plotted at the bottom here is a model calculation of Earth's, the amount of energy from the sun that the Earth receives at a particular latitude at a particular point in time. And what I have here is how that energy, the energy that we see from the sun, changes at 65 degrees north latitude on June 21st. Okay? That's the sun. So, different latitudes, depending on the time of the year, receive different amounts of solar energy. And I'm going to state something here. I'm going to show an analogy on the next slide. But there are ways that we can mathematically take things that look like this and figure out what the most important periodic components to them are. We see that these look cyclical. They look like they're changing with a pattern. But we don't know outright whether those changes are periodic. And we don't know if there are multiple processes involved in shaping that. And what we can do is, and I promise I'm not showing any equations, I'm just going to say that you can take things that look like this and have a way of interpreting them in terms of what periods are most important in making them up and how important they are relative to each other for a given signal. So when we take these, what are called insolation curves, so this is just describing how much energy we're getting from the sun, and this is at different latitudes. So this is June 21st at 0 up through 80 degrees north latitude. It's higher in the higher latitudes in the summer because there's more daylight each year, or more daylight during the summer. And when we do this mathematical analysis of things like this, you can see that we get these peaks, and these numbers on top of them correspond to the most important periods of the processes that are shaping those signals. 17, 19, 22.4, 23.7. What this is showing is that at all latitudes, there's some effect of that precession parameter on shaping how solar energy changes. At 41 and 54, we see at higher latitudes in the blue, obliquity seems to have a very strong role in shaping how that signal changes. At 98 and 127, you can't really see too well, but that's that eccentricity parameter. Doesn't seem to be quite as important as the others when we're looking at these records in this context. And there's another little hump here, which is 405,000 years, and I haven't talked about that yet, but we will. So I'm saying, this is some mathematical technique that we're using. The best way to think of analogies to this would be if I were able to play music. I wasn't sure if I was going to be able to play sound here, so I decided that I would just, this is in no way analogous, but to kind of think about what we're doing here, is you can imagine if there was some technique that we could look at a cooked dish and then get out the ingredients and how much there are. Or if we were to take a painting or some smear of colors and be able to say, well, what colors are there and in what abundance are they? We can do the same thing with these records of climate as influenced by changes in solar energy. So that's, I'd love to be able to play some music, but it's okay. So what's going on? How does this ultimately get encoded into the geologic record? So we have these changes, periodic changes in Earth's orbit that are affecting the amount of solar energy that's being received at a given latitude. That's affecting the climate in some way, and I'm going to be honest, depending on the climatic context, and in all climatic contexts, the exact way in which that happens is unclear because the climate system is dynamic. Things affect it in ways that you can't really predict. There are nonlinear processes that are going on. It's very confusing. But we know that it does because we can do tests like this and say, okay, well, I can see the effects of these changes, these very periodic changes. Climate's changing. That gets encoded into the depositional environment through some proxy that we can use, like that relative depth ranking that I showed earlier, but there are other ways in which we can try and understand that. And then those sediments that existed in the lake that were experiencing changes in the climate get buried, they get turned into rock, they get altered, so there's some distortion to that. What is the primary signal that might be recorded when those environments first existed are getting smeared, they're getting altered, and they're getting affected and potentially altering it to the point where we might not be able to say anything useful at all. So we have to consider that. And then we can do tests to see if whatever it is that we measured, that depth rank proxy that I showed you before, maybe some kind of changes in chemistry. We can take those records, do mathematical analysis on them, and then be able to test whether there is an orbital component to shaping the record that we observe, the proxy record that we observe. So what happens when we apply this approach to lake-level proxy data from the New York Basin outcrops? So taking the depth rank scheme, having that in your mind, which is, remember 0, the shallowest possible state the lake can be in, 5, the deepest possible state the lake can be in. Taking a record like that, like the one that we see at the Eureka Quarry. And also having some kind of age control, because I'm glossing over this, but if we were to just take these wiggles as a function of depth, the kinds of frequencies and periods that we can talk about are really only going to be how many cycles per foot do I see. I need some way of taking those changes in thickness and the cycles in terms of thickness and turning it into time. And before really good radiometric age control, when I say radiometric age control, I mean being able to date things like zircons in a lava and be able to unambiguously say what the absolute age is. This was done relatively. This was done counting, and I said that there weren't smaller cycles, but there are smaller cycles. If you look at the deepest water units that are present here, you can look at annual couplets called VARs and be able to estimate a sedimentation rate, which you could take that sedimentation rate, how many millimeters per year, and change that into years in terms of your measurements of the thickness of the rock section. So when we do that, and here's a couple more of these are called power spectra, what we see are lots of peaks. And those peaks all happen to correspond, when we take into account the age control that we've provided through the VARV counting, we see these numbers pop up. 22,000 years, 28,000 years, 22,000 years, 25, 100, 133, 22, 20, 28, 50, interesting, 23, 40, and 100,000 years. So when we apply this approach to these different sedimentary sections found in quarries and in outcrops, we can recover and test and demonstrate that there is a very strong component of orbital forcing that shape these records of lake level depth that we see in the record. Pretty cool. So what does that mean in terms of the basic Van Houten cycle that we showed earlier? That's 20,000 years. That is one of these Van Houten cycles corresponds to 20,000 years of time. And the average thickness of those cycles is about 4 to 5 meters, so about 12 to 15 feet. So to sum up where we are, I actually don't know how much time we have, so I'm hoping that I have a little bit of time. To sum up where we are right now, periodic changes in Earth's orbit affect climate, and this can be expressed in the rock record through cyclic changes in climate proxies. In the late Triassic, analysis of lake depth proxy records coupled with age models demonstrate that this observed cyclicity is consistent with the effects of orbitally based climate change. The periods of orbital components recovered from these proxies appear to not differ significantly from their modern values. And that's actually pretty important, is we see that things like the ice ages and glacial cycles, that 2,000-foot thick ice sheet that I mentioned to you before, I don't know if you remember, I said that went away 20,000 years ago. That's not a coincidence, right? But we actually don't have any reason to expect that those same periods that are operating on the climate system today should be the same 200 million years ago. So it's an interesting result that what we see today, what we see over the last several 100,000 years, also seems to hold true at these periods 200 million years ago. So why would we want a core? I think maybe you know the answer. Well, we could test whether these apparent orbital pacing that we see in climate as reflected in the cyclical leucospheric strata in outcrops, whether that occurs over the entire length of the record. These snippets that I showed you before are from discrete sections, no more than a couple hundred meters each, right? They don't give us an entire view of the length of the record available to us. There's about 30 million years worth of time in the rocks that are present in this record. We could test whether analysis of lake depth proxy records coupled with age models, I'm reading off a slide and not looking at what I'm saying. So we could test whether the periods of those orbital components are the same. Are they different? I said there's no reason to expect that they're the same. But when we apply it to 30 million years, do we see any changes in those periods? And what does that mean? And then from this record, we provide what's called an astronomically calibrated timescale. That's important because I mentioned before, lots of things are happening in the late Triassic. We don't have records. We have little snippets of records from the Triassic. We might want to have some common reference point to be able to correlate those records into. So if we're able to produce a timescale from this record, can we take a record from the United Kingdom or take a record from France and be able to say where it fits in unambiguously in geologic time? So that's what motivated something called the Newark Basin Coring Project, which lasted from about 1990 to 1993, and that was led by Paul Olson and Dennis Kent. And to show you, so that's us right there, that yellow star. The gold crosses are where these cores were taken. So you can see we're actually not too far away from the majority of where these cores were recovered. And these are just some nice pictures of the drill rigs. And you notice some familiar names: Rutgers, Somerset, Titusville, Margaret. Why? Because this is some of the best geology for understanding these kinds of processes. So pretty amazing. So if we kind of took a slice through the crust, through the Newark Basin, and see what these strata look like at depth, this is a very generalized schematic, we could see that the strata themselves dip and thicken towards the border fault. The cores themselves were drilled offset from each other to try and recover a complete, so they were drilled with overlap to recover a complete, or as complete as possible, as complete as the budget permitted, record of the sediments that are preserved in the Newark Basin. And when we stitch these records together, it's about over 14,000 feet of core, and that provides us with a set of cores that were collected by the Army Corps of Engineers back in the 80s around the Passaic River, gets us a complete record of the stratigraphy of the Newark Basin. This is where the cores are living right now. This is the Rutgers Core Repository. This is just one shot of the material that we have. The cardboard boxes that you see are housed, in this photo, maybe about half of the cores that were collected during that project. These wooden boxes, which are along the walls and in this room here that you can't really see, my laser pointer is, that entire room is filled with these wooden boxes. Those are cores that were collected by the Army Corps of Engineers in the 80s. And this is what the depth ranks look like in the cores. So you can see that there are changes in fabrics. You can see that there are changes in colors. And in terms of that depth rank scheme to try and classify rocks, you can see that there's things, maybe Paulson can do it a lot better than all of us and do it right. But if we learn the criteria that we need in order to describe these rocks, this is presumably reproducible. We can describe how these how the fabric of the rock changes and how that reflects the depth of the lake through time. Another important part, or another important component of this project was doing what's called producing a paleomagnetic record from these cores. There's a lot that we could say about this, but basically, the Earth's magnetic field flips directions. The time at which that happens is random, which is important because it allows us to produce a unique record of changes of how that of when that flipping is occurring. So this is what a sample from one of these cores looks like. A little plug is drilled into the core, and there's a method that looks at whether the magnetic field at the time that those sediments were deposited looks like the magnetic field today, or if it was flipped in the opposite direction. So these alternating white and black bars are just telling us what direction the magnetic field is. So if we have our record from the Newark Basin and a record from somewhere else, and we have some other age control, we can match these barcodes and say how they relate to each other. So producing this is very important to being able to correlate other records at the same time elsewhere in the world. And this is what the basic data look like. Sorry, this is very much squished on the screen, but what you see here are the lithological changes represented by the changes in colors for each hole. I can't even see here. Grain size, color changes, grain size changes. These are just the magnetic measurements here. That's how that translates to the barcode. So, to give you a sense of the scale and how much this adds to the record that existed previously from outcrop records, and really quarry records. This is that quarry section that we had before, the Eureka Quarry. And you can see that record extends from about 2,350 feet in depth to 2,500 feet in depth. And the total depth of this hole is somewhere around 3,000 feet. So you can imagine how this record can be expanded in either direction and how the thickness of those rocks is ultimately going to translate into the total amount of time that we're able to look at. That's just for one hole. And what we see when we start to go through these records is we see this basic pattern, the Manhattan cycle, repeating itself with some slight modulations, and you could probably see that in those photos I showed before, where you see these very prominent dark colored rocks that eventually become a little bit more muted as you go up through the succession, almost disappear and then come back again. And that first order modulation, which is the effects of the 100,000 year eccentricity cycle modulating the precession signal, is itself modulated by the 400,000 year eccentricity cycle. And all of these different cycles have to do with different effects of different planets, and that shape the geometry of Earth's orbit over very long time scales. So this particular 400,000 year cycle has to do with the interference of Jupiter and Venus on shaping Earth's orbit over 400,000 year time scales. And that turns out to be very stable throughout Earth history. But you can see, again, in the same way that this 20,000 year cycle kind of gets dampened, the expression of that 100,000 year cycle also kind of gets dampened as you go up through the record. And then that itself repeats itself and is modulated by a 1.8 million year cycle in the Triassic, which is interesting, because that 1.8 million year cycle in the Triassic, what we know from astronomical theory is that it should be 2.4 million years in the present day. The fact that it's different is saying something very real about what's going on in the system. And this is just another way of looking at the entirety of this record. So this is the entire chord record stitched together. The blue variations are depth rank. You see that most of the variability that you see is within this about 6 million year range, where we see these very pronounced changes in depth rank that get a little bit more patchy as we go into younger and younger sections. Almost disappears entirely at about 208 million years ago. And when we do these mathematical analyses, we can pull out these different cycles. And to get a sense of what this is, just a snapshot from about 220 million years to 221 million years ago, you can actually count out these little precession cycles and these small eccentricity cycles. And these larger arcs are the 400,000 year eccentricity cycle that we see showing up modulating that depth rank proxy. This is ultimately the time scale that is produced from that record. And you can see here, these are the different core records, these are the depth ranks, these are the magnetic barcodes. They're correlated to each other. You can see me matching these black bands to each other, black or white bands to each other. And taking thickness, translating it to time, there's now a record that you can have, and you can count out in terms of that 400,000 year cycle all the way back to about 226 million years ago. So just in terms of how that 400,000 year cycle shows up and modulates these smaller, higher frequency cycles, you can start at about 199 million years ago and actually walk out that 400,000 year cycle in the course, which is pretty cool. So how can we test if it's accurate? I'm not going to get into this, but that motivated a whole other coring project, something called the Colorado Plateau Coring Project, which drilled into a contemporaneous sedimentary section where there were ashes that could be dated and a magnetic stratigraphy that could be produced. So from the magnetic stratigraphy, being able to be correlated into this record with ages, we can test whether that timescale from the New York Basin is accurate, and it is, and I'm not going to get into the details of that. So what else have we learned about ancient climate by studying these records? So turns out you can produce a CO2 record for the Triassic from these records, looking at soil carbonate nodules, and we might see some of those on the trip. We could certainly see where they were on the trip and some of the rocks. And this is, again, something that we can't get into the details of, but by measuring the carbon isotopic composition of these little nodules that form in soils, which are in equilibrium with the atmosphere, we can reconstruct what the concentration of CO2 was in the atmosphere at the time those soils existed. So from that, we could see that in the Mesozoic, CO2 is a lot higher. Anybody know what CO2 is right now? About 400 parts per million in the atmosphere. We're looking at about 10 times higher atmospheric concentrations of CO2 in the Mesozoic than today, which actually went down during the Mesozoic. And you see this whole mess of data right here that's all collapsed in the sedimentary record right around the eruption of those lavas that I mentioned to you before. And what's happening is those volcanic eruptions are happening, all kinds of gases are being emitted into the atmosphere, CO2 concentrations are increasing, and that also shows up in the record. And we can see this, we can see the CO2 story translated into depth ranks in terms of how variable the hydrological cycle is. We increase CO2, we increase the strength of the hydrological cycle. That changes the expression of this external cyclicity that's encoded in a rock record in terms of lake level depth. And at times of highest CO2, you can see that's where most of the variability is in that lake depth record. As CO2 is going down and is variable, the lake depths are also variable in terms of how that's expressed hydrologically, in terms of how that's expressed hydrologically as a function of climate, as a function of how CO2 is modulating climate. And then when CO2 is at its lowest, that's also when we see most of that variability reduced to nothing. And that shows up in the cores. And these don't show up too well, but the oldest parts of the core are mostly river sediments, and that's more of a tectonic control than a climatic control, and show up as these large sandstones. But you can see the colors of the rocks at times of high CO2 are much darker and much richer. And then as we go younger, we kind of get this gradual reddening and not much variability in the rocks. So, Sean, you're telling me there's all these climate cycles and we have astronomical processes that are shaping climate, but can we say something about what the solar system is doing? It turns out that we can. And this gets back to that 1.8 million year cycle that modulates the 400,000 year cycle that I mentioned before. And I mentioned that was different than what's predicted from astronomical theory for today and what's actually observed today in different climatic records in the ocean basins, for example. And this is a little movie And there's a whole message. I said I wouldn't show any equations. These aren't equations. But the important thing to note is that we talked about these changes of eccentricity, tilt, and precession. There are other things going on, like how is the orbital plane of the Earth moving around the sun in the plane? How is it tilting? How is it wobbling like that? And it turns out that we can, I'm just going to say it again, say this, we can empirically determine these values from the proxy record, and by being able to say how these change, what the frequency of these changes are of the frequency of the precession of perihelion, and we can estimate these Milankovitch cycles, and if we have a long enough record where we can look at this over a long enough period of time, all we need to do is measure some of these things in our record, and we can solve systems of equations to estimate the others, and be able to get at empirically determined values for all of these letters that you see here. And what those letters are describing are these changes for other planets. And we've done this to a first order, looking at this record. And this is, again, just showing records from the Newark Basin. And you can see these periods that pop up on the power spectrum: 94,000 years, 99,000 years, 122 and 23. It's that eccentricity cycle. And you can see over here, this 1,724, that's the 1.8 million or 1.7 million year modulation of the 400,000 year cycle. And you can see, looking at climate records from the modern, going back to about 22.4 million years ago, that's different, 2,340. This looks like somebody threw multicolored pasta at the wall. But what this is describing is the period of that 2.4 in the modern and 1.7 million year period in the Triassic, showing different astronomical solutions that attempt to describe that through time. Starting at 0 and going back to 50, all of these solutions agree with each other, they converge. But after about 50 million years ago, they all say something different. But what our record allows us to do is be able to look at how that changes through time, the time that's available to us. And we need the right kind of record. We need something that has a high enough resolution to be able to look at very fine scale changes in the climate through the different kinds of proxy records that we can produce. So, some remaining questions. Are there any proxy records that we can recover from the climate signal in this record? Maybe. If yes, can those proxies recover the climate signal from time intervals where no apparent variability exists in depth, rank, color, etc.? And if we can recover and generate a climate proxy from these intervals of low variability, can we, and demonstrate an orbital component, orbital pace component, can we place empirical constraints on solar system dynamics, and how can we further extend our much broader understanding of how CO2, tectonics, and all of this shapes the Earth at this time? So, what we did a couple years ago is we did some tests. We went to some of these sections of the record that had very high variability in terms of that lake depth proxy. We went to some sections that had very low variability in terms of that lake depth proxy. And we produced chemical records. And this is something that sounds, I just go sample and measure the composition. When you have 7 kilometers of rock, that's a lot of samples to take and be able to measure through traditional techniques. What we did was core scanning XRF, which allowed us to look at how those changes occur continuously and let us get at it much more rapidly. And this is the basis of the project that we're working on right now at the Rutgers Core Repository, producing chemical records through the entirety of this section to try and say something about how those changes in the chemistry, as reflected, as they're reflecting changes in climate, as the changes in climate are reflecting changes in these astronomical parameters, to be able to take what we observe and be able to say something about ultimately the, is that me, guys? Okay, so I know I'm running late, but there's a lot that I wanted to get through. So this is laid out. These are students working in the lab. This is what all these cores, not all these cores, a very small fraction of these cores look like when they're laid out on the table. You can see these beautiful textures that are in the rock. Kind of very much like a hospital, like a hospital in a warehouse. And this is putting cores in the instrument. And these are what these records look like. These are, do I have depth on here? Yeah, meters. So this is almost 1,000 meters of core. This is just one hole. And what we had to do to optimize our ability to detect the widest array of elements possible is we had to measure each of these cores twice. That's also good for reproducibility too. I'm not going to get into the details of this. But to give you a sense of the number of measurements that we've made on these cores, each hole has about 100,000 measurements times 2 times 7. So we're upwards of 1.5 million measurements that we've made for this project looking at changes in chemistry through this record. This is just another hole. And we're also doing the same thing for that record from the Colorado Plateau, both looking at how changes in chemistry are reflecting changes in climate, but also being able to map things like arsenic and uranium in the bedrock and saying something about the conditions of the aquifer that might mobilize those elements and end up into drinking water, for example. So we're chugging along on this. We're producing large data sets, doing a lot of data analysis. So we'll hopefully have some pretty interesting results soon. We're also doing more cores from other records, different places, trying to further extend both the latitudinal swath that we're looking at climate over, as well as extending the range of time. So we have a couple of coring projects that are planned, one out west on the Navajo Nation in southwest Utah. We have a couple sites selected, and at Dinosaur State Park in Connecticut. There's one part of that trackway, so please go check it out. So what interesting geologic, that's why you're here, right? And I know it's a long lead up to some of this, and this is just going to be very much an appetizer. So again, this is the Newark Basin, a much nicer colored version of the map, and you can see there's these different colored units, and they correspond to different rock formations. The colors correspond to different rock formations. Those different rock formations formed at different periods of time. We're going to zoom in on the area around us, which is approximately where that blue star is. And this is what the geologic map looks like. Again, I didn't choose these color schemes. These are from the official geologic maps. And you can see that we're kind of complicated. I actually don't know if there's a color difference between here and here, but I know that there's a rock difference. And you can see all these lines that are cutting across the map. Those are all faults. So the rocks that formed here in these lakes, after they were deposited, they were all chopped up by tectonic forces. I mean, to some extent, we actually don't know when some of these tectonic events happened, or how much material may have been here before we see the present day landscape. There's estimates that as much as 5 kilometers of rock may have existed in this record that was subsequently eroded offshore during the Jurassic period. So there's a whole chunk of this record that might very well be missing that we don't see in the present day. If we were to kind of take our knife and cut into the rock like we would a cake, this is generally the kind of cross-section that we see. And this is very similar to what I showed you before, that generalized the cross-section of the entire Newark Basin record before. You see this fault here, this is the Hopewell Fault, and you can see at the surface, this is reflected by the juxtaposition of older rocks on one side, and you walk to the southeast, and you have younger rocks. And we're going to see that fault on the trip next week, May 6th. May 6th or 7th, rain date. But there's all kinds of other interesting features. These pink blobs here are, that's the San Juan Mountains, that's the Lambertville Sill, and this is also, these are igneous intrusions that exist at depth. This darker color red here is a lava flow. So this color here, magma that never made it to the surface. This color here, lava that did, extruded on top of these lake sediments. If we strip away the geologic map and we strip away the vegetation, we can look at a LiDAR image of this. Again, here we are in the yellow star. And we can see some, really the only remnants of human activity that we can see here that pop out at us are these quarries, right? Which if you go back here, and I'm sorry that this isn't, I put this in 5 minutes before I left, because I thought it was a nice cross-section. But those quarries are right on top of those igneous intrusions. So that the core that's circled there is the Sylvie core, and this is what it looks like on the inside. We may go there on May 6th. Hopefully we go there. And for whatever reason, the last couple times I've been out in the field, I haven't been taking great pictures, so I apologize. But you can see some rhythmic bedding here. You can see a little black shale popping up here. This is actually right below that igneous intrusion. So these are metamorphosed sediments. This is a rock type called hornfels. It's a metamorphosed sedimentary rock. And you see, this is much smaller scale. That's the length of a rock hammer, maybe my forearm in length. And yeah, there almost appears to be some cyclicity here. Whether that's external or astronomical in origin, probably not. But it's interesting to see these patterns of cyclicity at different scales as well. And this is a very deep lake that existed here, as evidenced by the very fine laminations that are still preserved after they were thermally metamorphosed by the sill. This is higher up in the quarry. This is looking at the igneous intrusion itself. You can see from a distance, not that you would really be able to see all that much anyway. This is much more massive rock. You don't have layers. These are not sediments. This is magma that cooled and crystallized at depth. So an analogous place, and maybe one that, certainly one that has better exposures if you don't have access to a quarry to go into, is the Palisades Sill. And these are the cliffs that you see coming into New Jersey, coming across the George Washington Bridge from New York City. This is, again, a fossil magma chamber that intruded into the crust at the same time as the Lambertville Sill, which makes up the Sauerland Mountains, and was the plumbing for the first eruption of the Central Atlantic magmatic province that we see here. So these are, much more dramatic cliffs that we see. This is at the state line lookout. This is looking north along the Hudson River, sometime in the winter. And, we go below the sill, we can see the same lacustrine strata. This is maybe 10 meters below the sill. Very similar to the kinds of rocks that we see in the Sylvie Quarry. That's me last week, standing at the sill, looking at the contact between these rhythmically bedded sedimentary rocks and the igneous intrusion that kind of shoots up like a jelly donut into the lake beds. They're rocks at the time this is happening. So geometrically, three-dimensionally, what does this look like? You can see these magmatic sheets. When we call them magmatic sheets, these horizontal sheets, we call them sills. When they're vertical and cutting perpendicular to the rock layers, we call them dikes. There's all kinds of, geologists love words. So I mentioned to Candy when we first met on this trip, if you ever read Annals of the Former World by John McPhee, there's 2 pages, somewhere around like page 50 something, where he has 2 pages of just all the different kinds of words that geologists like to use to describe things. And it's really, really pretty funny. But the point that I like to make is just that in the Newark Basin here, we have preserved a fossil magmatic plumbing system. The Lambertville Sill and Sauerland Mountains, the Palisades Sill. All of these, if we go look in this area in the Newark Basin, right there, this is at the Chimney Rock Quarry in Bound Brook, fed the first eruption that we see in the Newark Basin associated with the Central Atlantic magmatic province. And you can see the bottom of this picture, not quite well. It's hard to see the cyclicity here because this is all red, but you can see layered rock, shallowly dipping, and then right above it, it gets more massive, and the contact is somewhere right behind this little shed right here. You can see the lava erupting onto the fossil lake surface. This is just another view of it. And again, this is one lava flow, one magmatic plumbing system of this massive province that existed 200 million years ago. Again, coincides with the Triassic mass extinction. And we have very good age constraints on this from both our understanding of how climate is paced astronomically in the sediments that these lava flows are erupted onto, as well as from zircon, uranium, lead geochronology. And again, I said before, after each eruption, we see these spikes in CO2 that happen. And that's just evidence of outgassing of CO2 at the time of these eruptions. That's actually really complicated in terms of what's driving extinctions, especially on the land. It's a very interesting story I can't get into, but if you want to talk more about that, it has to do with feathered dinosaurs.
Can I have your attention, please? The library will be closing in 15 minutes.
I know I'm going way over time, but hopefully this is good and informative for everybody. So I'm ending right now, actually, and this is probably the most interesting part. So, the yellow star is us. We strip away the vegetation again. We look at that little rectangle just to the northwest. And what do you see? Rhythmically flowing hills, undulating hills. And what those rhythmically undulating hills are representing, and this is that eccentricity curve from before, those hills and the topography, because they're made of rocks, which were sediments deposited in this lake that's modulated by climate, which itself is modulated by these astronomical cycles, reflect the changes in orbital processes that ultimately shape the climate. So, if you want to see more, come join us. And so thanks to everybody. I want to say, you could probably guess, just based on the scale of this thing, this is very much a team effort. A lot of the projects that we have a lot of students working on these projects with undergraduates and graduate students, and the kinds of things that we're doing would not be possible without them. And I think they have a good time. Especially finding nice continuous pieces of core in the boxes, and we've also started an informal stickball league. So if you like playing stickball, come up to Piscataway. So anyway, thank you.